Welcome to this explainer. Today, we're tearing down the black box of hardware to solve a massive AI scaling problem together. If you've been wrestling with huge data sets, just desperately trying to squeeze every last drop of performance out of your infrastructure, well, you're exactly where you need to be.
We're coming at this from a highly specific angle today. Look, I'm a memory hardware architect, and I'm talking directly to you, the AI software engineers out there. You build the algorithms, I build the pipes. So let's tackle the ultimate systems question together. When exactly should your data live in DRAM versus flash?
Here's our roadmap for today. We'll hit 1. The 5-minute rule dies. 2. AI's extreme memory demands. 3. The new break-even framework. 4. Real-world bottlenecks. 5. From minutes to seconds. And finally, 6. Rethinking AI software design. All right, kicking things off with Section 1, the 5-minute rule dies.
Let's absolutely shatter a fundamental assumption you were probably taught back in your systems classes. Way back in 1987, Jim Gray's classic 5-minute rule dictated caching strictly on hardware economics, basically weighing DRAM rent against disk fetch costs. And hey, even with updates in 2019, that heuristic kept the DRAM to SSD threshold at the minute scale. But looking at 2025, AI's petabyte-scale working sets and wild access patterns have completely obliterated that old rule. The purely economic view just totally ignores host costs, feasibility limits, and how modern workloads actually behave.
Moving to Section 2, AI's extreme memory demands. To understand exactly why that old rule broke, we have to look at the extremes of modern memory powering today's AI. Check out this top-tier setup, Micron's HBM3E. See how the memory is physically packaged literally right next to the host processor? This system-in-package, chip-on-wafer-on-substrate magic is engineered for absolute maximum compute performance by shrinking the physical distance the data actually has to travel. The sheer performance density here is just wild. HBM3E is an absolute beast for AI workloads. We're talking an industry-best data rate and over 1.2 terabytes per second of bandwidth. Plus, it gives you a 2.5 times performance per watt improvement over older generations. Super energy efficient. But, and this is a massive but for you software folks, its physical capacity is strictly bounded. You get 24 gigabytes in an 8-high cube. That's the limit. It is blindingly fast, but severely cramped on space.
Which brings us to Section 3, the new break-even framework. Because that top-tier DRAM capacity is so incredibly limited, we literally have to start using flash as an active memory tier, not just some cold storage locker. And to do that right, we need a new math framework. Think of it like rent versus commute. Keeping data in DRAM is like paying premium rent to live downtown next to the office. Fast, but very pricey. Fetching it from the SSD, that's the cost of commuting. If you need the data all the time, pay the high rent. But if it's less frequent, commuting from the SSD makes way more sense. We just have to pinpoint the exact break-even interval where those two costs balance out.
So how do we actually calculate this commute cost? Well, we balance the DRAM capacity rent against 3 real-world commute taxes that your software triggers. First up, the host processor cost, because every single I/O eats up CPU or GPU cycles and interrupts. Second, the host DRAM bandwidth cost. Transferring data into DRAM hogs precious bandwidth. And third, the actual amortized cost of the NVMe SSD access itself. That old 5-minute rule we talked about, it completely ignored those first 2 host costs.
Let's dive into Section 4, real-world bottlenecks and limits. Now for the constraints. As a hardware architect, I'll let you in on a dirty little secret. Vendor peak IOPS on a datasheet, yeah, they're essentially a lie in the real world. If you design your software assuming you'll get maximum datasheet IOPS, your system is going to bottleneck instantly. We have to swap out theoretical datasheet peak IOPS for feasibility-aware IOPS. That means we explicitly bound the SSD's capabilities by your processor's actual IOPS capacity, your host DRAM bandwidth limits, and your application's strict tail latency targets. Take a look at this first principles view of the I/O path. True performance is bottlenecked by several physical realities. You've got the controller translation bandwidth, the NAND sensing latency on the individual dies, and the PCI interface limits. So, for example, if your software is firing off tiny 512-byte requests, the system gets bottlenecked by the processor's ability to issue commands and the SSD controller's ability to translate those logical addresses. It's not actually limited by the raw bandwidth of the PCI bus. Let's see how latency targets actually restrict you in practice. Say you're building an AI serving pipeline with super strict latency needs. If you enforce a 99th percentile read-tail latency of 13 microseconds for a 512-byte block, that actually caps your usable SSD utilization at about 90% of its physical peak. Try to push it to 99% utilization, your tail latency absolutely explodes up to 85 microseconds just from queuing delays. You just can't use all the IOPS if you want predictable, low latency. All right, section 5, from minutes to seconds. So when we finally plug these real-world constraints, the processor IOPS limits, DRAM bandwidth, and latency targets into our framework, the math completely flips. The whole paradigm shifts. If we plot a traditional CPU platform against a modern GPU platform, the difference is just staggering. CPUs have a limited IOPS budget, maybe around 100 million IOPS. But GPUs, they have massive IOPS budgets, upwards of 400 million, plus immense GDDR bandwidth. Because GPUs can actually process the I/O fast enough, they shove that DRAM flash caching threshold all the way down for minutes into the single-digit seconds regime. And you can see that collapse vividly right here. For GPUs paired with modern storage-next SSDs, across 512-byte to 4 kilobyte block sizes, the break-even interval plummets to below 7 seconds. Think about what that means. If your data isn't going to be touched again in the next 7 seconds, it is economically optimal to evict it from your precious HBM or GDDR and just fetch it from the SSD when you need it. Flash is no longer cold storage, it is active memory. Which leads us to our final part, section 6, rethinking AI software design. This massive hardware shift means your AI software needs an immediate architectural rewrite. You simply cannot write code for a second-scale memory tier the same way you did for a minute-scale storage tier. Take approximate nearest neighbor search, a totally core component of AI retrieval. Instead of caching massive gigabytes of full vectors in DRAM, you can now fetch a tiny 512-byte reduced dimension vector directly from the SSD, do a quick distance check in the processor, and only grab the full 4 kilobyte vector if it actually passes the threshold. You're trading abundant SSD IOPS to save incredibly scarce DRAM capacity. To truly leverage this new reality, your software has to step away from those huge block transfers. Step 1, start exploiting ultra-high random IOPS at small block sizes, like 512 bytes. Step 2, design for fine-grained access and massive concurrency to keep those GPU IOPS pipelines totally full. And Step 3, embrace sparse stat structures. Flash is cheap enough for gigabytes now that you can actually afford to over-provision on the SSD if it simplifies your software's access patterns. We've basically handed you a memory tier that operates in seconds rather than minutes, fundamentally blurring the line between memory and storage. The hardware is ready, the math is proven, and the real-world bottlenecks are mapped out. So, the ultimate question I want to leave you with today is this: what completely new AI algorithms are you going to build to exploit this? Thanks so much for joining me on this explainer, and I really can't wait to see what you engineer next.